lot of different techniques about how to find limits, whether they be limits as x goes to infinity or a negative infinity. We've talked about how to find limits if you have a removable discontinuity or a hole, and went over a ton of different techniques for that. We've looked at finding limits from tables and graphs. So today we're going to go over infinite limits, or how to find a limit if you have a vertical asymptote, or a non-removable discontinuity. And we're also going to go over laws of limits, or limit properties. Now, these two probably could have been two different lessons, but they would be so short that just combine them. So we're kind of going to do two lessons in one today. So let's start with the properties of limits. And I think these properties you're going to find are pretty intuitive. They're not too tricky, and they work just like I think most people would think they work. So here's a list of all of them. I'm not going to make you write them down. And they look a little bit more complicated than really what's going on here. So the scalar multiple property just basically says if you're taking the limit of an expression that has a multiplier, so like let's say it's like 3x squared or something like that, you can factor out the 3 or that coefficient outside of the limit when you compute it. The sum or difference property just basically means like if you are finding like the limit of the sum of two functions, you can find that limit of each function individually and then add those limits together. All right, that's basically what this is saying. If L is the limit of f of x as x approaches c, and k is the limit of g of x as x approaches c, then the limit as x approaches c of f plus g is just the sum of the limits. So you can find the limits separately, which is really nice. You don't have to find it all together. Same thing's going to go for product and quotient, and even the power rule is really just an extension of the product property. It's the same thing. The only little catch here is with the quotient property, you can't divide by 0. So if that function has a limit that equals 0 in the denominator, then you'd say that limit overall doesn't exist because you can't divide by 0, which you might suspect that anyway. So let me show you just a couple of examples that utilize these properties. Here's a couple of piecewise functions, and we can use the graph to determine these limits. So this first one says the limit as x approaches -2 of f plus 5g. So I'm going to start off by writing it out exactly how this breaks down, but I think you're going to be able to skip that first step pretty quickly. That's where you don't have to write that down. So basically what we can do is we can split up these limits. We can write this as the limit as x approaches -2 of f of x plus 5 times the limit as x approaches -2 of g of x. Now, as you're trying to evaluate this, really what you want to do is say, okay, well, let me find the limit as x approaches -2 of f of x, and that's going to be what this equals. And then the limit as x approaches -2 of g of x, if I figure out what that equals, multiply that by 5 and add them together. It works just like how you might think it would work. Yeah, there's not really anything too weird here. So let's evaluate these limits. So what is the limit as x approaches -2 of f of x, which is this left one? Yeah, it's 1. Okay, it's 1 because the left and the right hand limits both agree. That has to be true for a limit to exist. The left hand limit has to equal the right hand limit, which we see it does. What's the limit as x approaches -2 of g of x? Oh, g of x is not even labeled as g of x here. My bad here, y'all. Let's call this g of x. Make a little note that I need to throw that in there. So yeah, what's the limit as x approaches -2 for that one? Yeah, -1. This function is continuous at -2, which again, we have not formalized continuity yet, but hopefully you're starting to think about what that might mean for it to be continuous. But anyway, yeah, so that's going to be -1. So we have plus 5 times -1 equals, well, -4. So it may be that kind of once you get your head around how you can split up these limits, evaluating these limits can go a little faster. right? Because we already know now what the limit as x approaches negative 2 is for both f and g. So if I want to find the limit as x approaches negative 2 of f divided by g, I can just divide those two limits. Right? I already know what the limit of as x approaches negative 2 is. It's 1. And the limit as x approaches negative 2 for g is negative 1. So this would just be negative 1. Any questions so far? What's the limit as x approaches 1 for f of x? Yeah, it's 2. So this is going to equal 2 times the limit as x approaches 1 of g of x. Yeah, what is the limit as x approaches 1 for g? Yeah, why not? There's a skip. Yeah. Tell me why in terms of limits. Yeah. What?
As it approaches from the left side and the right side, they don't get really close to the same point.
Right. The left and the right hand limits are not equal, right? The left hand limit equals negative 2. The right hand limit equals 1. Since those are not the same, you say the limit doesn't exist. So we have 2 times does not exist. It just does not exist. Yeah. Oh, D and D. What am I doing here? So yeah, this does not exist. Okay, now what about this other one? Okay, so this is a little different because we've got a function that is not graphed, 3x. But what is 3x approaching as x gets closer to 1? 3. Yeah, 3x is just a line, right? It's continuous. So the limit will exist everywhere, or there will be a limit everywhere. So you just plug in 3. You can use direct substitution on that one. So yeah, we've got 2 plus 3 times 1, which is 5. So that's how these properties work. You can see how we don't really need a whole day to go over this, I think. Let's do just a couple more examples, and then we'll talk about infinite limits. Yes, ma'am. The last one? Okay, sure. Let me show more work and maybe to kind of clear that up a little bit. So if we use that property, that sum property, we can split up the limits statement and say that the limit as x approaches 1 of f of x plus 3 times the limit, or we don't even, we can evaluate this without even splitting it up. We'll just say the limit as x approaches 1 of 3x. So the 3x is like another function, right? It's not graphed here, but you know what 3x looks like. Yeah, it's just going to be like a line, does something like this, right? And if you're trying to find a limit at a point for any function that's continuous like this, where there's no breaks or gaps in the graph, you can just use direct substitution. And so you can just substitute in 1 into x there. So I've got the limit as x approaches 1 of f, which we've already just, shown to be 2. Well, you can see that over here. And then we can use direct substitution on that next one. So 3 times 1. And so that's where we're going to get the 5. Does that make sense? Yeah. So just because the function's not pictured doesn't mean you can't evaluate the limit necessarily. All right, so this says assume, we don't know what f and g are, but we do know a single limit of them. So we know that the limit as x approaches 4 of f is negative 2. And of g is 3. So all of these are going to be limit as x approaches 4s. So it should be like pretty easy, I think. This might be one of the easiest things in this whole unit. So the limit as x approaches 4 of g of x, what does that equal? Yeah, 3. It's defined right here, right? So this is going to be 3 plus 3 is 6. Okay. What's the limit as x approaches 4 of just x? That's not pictured here. But if we have just like y equals x or f of x equals x, we want the limit as x approaches 4. What is that? Yeah, it's just 4. You can use direct substitution, right? So this is going to be 4 times the limit as x approaches 4 of f of x, which is negative 2. So this will be negative 8. All right. What's the answer to the next one going to be? See if we can just go straight to it. 1. Yeah. So the limit of g of x as x approaches 4 is 3. And the limit as x approaches 4 of f is negative 2. So yeah, you get 1. Fit this last one in there. So we've got 5 plus 4 times f of x. So the 5 is just a constant function, so that's just going to remain 5. Plus 4 times, well, the limit as x approaches 4 of f of x is negative 2. Throwing some equal signs here. So we get 5 minus 8 is negative 3. Any questions about this? Any of these limit property problems? These limit laws? All right, let's talk infinite limits. Okay, so this is something that we've kind of hinted at. We've looked at limits at asymptotes if I give you a graph, right? So when we were trying to compute limits, like really before today, and the value was going to be undefined if we tried to direct substitutions. What happened for the most part was if you plug in the number, like let's say I have the limit of x approaches 2 of like, oh, no, let's do x plus 1 times x minus 2 over x minus 2, right? Something like this. If I just try the direct substitution, it's going to be undefined, right? Because I've got a hole here. And the point I want to make is we know that it's a hole because not only does 2 make the denominator 0, but it also makes the numerator 0. So if you try direct substitution and you get something like 0 over 0, that indicates that you have a hole. That's where you want to try to manipulate the equation and cancel out that factor to remove the removable discontinuity. Now, if you try to do direct substitution and it makes the denominator undefined, but not the numerator, so it's just the denominator that's 0, then that's going to indicate we have a vertical asymptote. So when you have a vertical asymptote, let me just erase this, clean this up a little bit. I'm going to show you kind of 4 different cases here. So say, I've got something like this. I'll draw four little dotted vertical lines here, so you can just kind of see the different, what could happen here. Like if you just have your parent rational function 1 over x, then as you approach that vertical asymptote, it goes down to negative infinity on the left and up to positive infinity on the right. So in this case, I would say the limit doesn't exist. The left and the right hand limits don't match up. If I were to simply ask, what's the value of the left-hand limit, I'd say negative infinity. Even though technically it doesn't exist, I'd still want to say which direction it's going. If I were asking for the limit from the right, I would say positive infinity because it's going up, positive infinity. But if I were just asking for the limit itself, I would say it does not exist, particularly because they're going 2 different directions. So it could do something like that. It could also do something like this. Same kind of idea here. Oh, nope, not like that. Let's try to redraw that. And this is kind of a very similar scenario where the limit would not, you just say does not exist. Yeah, we're just going up one way, down the other way. But it is possible for, like on both sides, like if you have 1 over x squared, for instance, on both sides of the asymptote, the function is going up to infinity. And while it's true that the limit doesn't exist, in this case, I would want you to say it's actually going to infinity because it is going up on both sides. Okay, so technically it doesn't exist. Yes, that's true. But to be more specific, I want you to say, yeah, it's going to infinity. And then you might imagine what the only other option here is if it's going down on both sides. In this case, we would say negative infinity. Now, we can't use those algebraic tricks that we did before because we're not going to get any factors that cancel out. Like if we look at this first one, nothing's going to cancel here, right? You can't factor or really do any algebraic tricks to force that to factor or to cancel. 3 does make the denominator 0, though. Like if I try direct substitution here, I get something over 0, but that's not something. And that's going to indicate a vertical asymptote. So now I need to determine, okay, I know there's a vertical asymptote. I already know that the limit's not going to exist, but I also want to be able to tell, like, well, if it doesn't exist, is that because the limits aren't the same on both sides, or is that because we have this unbounded behavior towards infinity? So what we have to do is basically plug in some values here. See what's happening very close to the asymptote. And we don't really care about like evaluating it exactly. We just want to know like, well, is it positive or negative? Is it going up or down? So let's test 2 values. Okay, so let's test like a number right before 3. So something like 2.99. Okay. This is going to give us the limit from the left. Okay, so this is going to give us the limit. You don't necessarily have to write this on everyone, but we want to do the limit from the left. We're just trying to find some evidence of if it's going to positive or negative infinity. So let's go ahead and plug in 2.99. Now you're not going to get a calculator to evaluate this. And remember that you don't really need to know exactly what it equals. You just need to know if it's plus or minus. Is it positive or negative? So this is going to be the numerator. It's obviously positive because we're adding 2 positive numbers together. And the denominator is going to be negative. Because 2.99 is smaller than 3. So what's the limit as x approaches 3 from the left? Negative infinity. Yeah. Okay, so now we know it's going down on the left-hand side, right? If this is my vertical asymptote, I know the function is going down this way. But now I need to determine what's going on the other side. So what might be a good number to test to find the right-hand side? 3.01 would be good, sure. Right, barely to the right. So let's go ahead and test that out. So 3.01 plus 4 over 3.01 minus 3. Yeah, that's going to be a positive over a positive, right? So we can say that the limit as x approaches 3 from the right is approaching positive infinity. So we have like this test we're doing, and then this test. Now, you don't necessarily need to show every step here. I mean, you're just trying to figure out what's going on the left-hand side and the right-hand side. And if you can just like, do it in your head, so to speak, and just make this statement right here, I'm fine with that. Basically, you're just trying to communicate what's going on both sides of the asymptote. All right, so what's the overall limit? Yeah, the limit doesn't exist. So the limit as x approaches 3 does not exist. Oh, let's go ahead and I didn't write the actual function there. X plus 4 over x minus 3 does not exist. Any questions about that one? All right, let's try to do the next one. If you tried direct substitution here, 5 is going to make the denominator 0, but it doesn't make the numerator 0, so we've got a vertical asymptote as opposed to a hole. You'll get a hole if it makes the numerator 0. All right, so if this is my vertical asymptote, I want to know what's going on the left and the right. So let's find the limit as x approaches 3 from the left. So what might be a good number to substitute in here? 4.99. Yeah, so 4.99. Okay, so yeah, maybe we test 4.99. So we're going to plug that in. Obviously, it's going to make the numerator positive because 4.99 is positive. And actually, since this is squared, it doesn't even really matter what you put in here because squaring a number is always going to make it positive. So the denominator is going to be positive also. So on the left-hand side, this limit is going to positive infinity. So now let's test the right-hand side. Although because of the, how this is set up, you might already know what it's going to be. But let's test a number like 5.01. Just barely bigger than 5. Well, if I plug that into x, that's going to be If I plug that into x, that'll be positive. And anything squared is going to be positive, so I don't really care what's on the denominator there. And so the limit as x approaches 3 from the right will be also positive infinity. So we get this kind of behavior at that asymptote.
Why is it x approaches 3?
Did I say 3? Oh, I don't know. Yeah, good catch. Yeah, no, that should be 5. I'm sorry. Don't know why I was writing 3. Maybe I was just copying the other problem and talking too much. Got a bad habit of that. All right, so we've got our two tests. We've determined the left and the right-hand behavior. So while it's true that the limit's not going to exist here, and the limit will never exist at a vertical asymptote, so I'm not really, so you could say it does not exist, but really what I want to know is plus or minus infinity if it's appropriate. So since on this case, it's going to positive infinity on both sides, we're going to say that the limit as x approaches 5 is positive infinity. Any questions about that one? All right, let's do a little mixed practice here. I want to keep throwing some of those older limits at you. I don't want you to forget about how to find an infinite limit, or how to find a limit at infinity, I should say. Okay, let's talk strategy here. This first one, what should be your number one instinct anytime you've got a limit? Direct substitute, yeah. Try direct substitution first. If it works, great. If it doesn't, we'll find another strategy. But here, if I just plug in 6, then I have got no issues. It's not going to be a divide by 0 problem or anything like that. So this is just going to equal 6 plus 2 over 3 times 6 plus 12. So 8 over 18 and 12 is 30. Yeah. It should be 4 over 15, although I'm fine with you writing 8 over 30. 8 over 30 is a great answer. Perfect answer. All right, B. Can we plug in 6? No, and if we try to, we're going to get 0 over 0, right? So if we get 0 over 0, what does that indicate? It's a hole, which means we need to go and try to cancel out that hole, remove the removable discontinuity. And we can do that through factoring. So we can factor the numerator with the greatest common factor being x. And we can factor the denominator. Since it's a difference of 2 squares, it's x plus 6 times x minus 6. And this is how we're going to remove the removable discontinuity. Just cancel out those x minus 6's. And now we can use direct substitution. So it's going to be 6 over 6 plus 6, which is 1/2. Or 6/12. Same thing. All right. So yeah, the first one, there was no zeros, right? So that means use direct substitution. All right, if you get something that's not 0 over something that's not 0, then just use direct substitution, no problem. Get 0 over 0, there's a hole there. Now, if I plug in 6 to the last one, it gives me a 0 on the bottom, but not the top. So that means we've got a vertical asymptote. And so now we're interested in what's happening on either side. So let's find the left-hand limit. What's the limit as x approaches 6 from the left? So what would be a good number to test?
5.99.
Yeah, 5.99. Okay, if I plug in 5.99, into the top, into the numerator, this will be negative, right? Be negative. If I plug in 5.99 to the denominator, I'm raising this to the 4th power, so that's always going to be positive. So I've got a negative over a positive, which is negative. So the left-hand limit's negative infinity. And if I test the right-hand limit, by plugging in something like 6.01, again, we get a negative on top, a positive on the bottom. So that's also going to be negative infinity. And since those two are the same, we're going to say that the limit as x approaches 6 of negative 3x over x minus 6 to the 4th is negative infinity. And that's it for today. Yeah? So went over the properties of limits, looked at vertical asymptotes. We've talked about all the limits we need to talk about at this point. Next time, we're going to talk about continuity. We're going to finally formally define what it means for a function to be continuous. We'll go over like the different discontinuities, which we've already talked about a lot. So it won't be a whole lot of new stuff. We're just going to formalize it and kind of put it together in a note page. And that's going to be it for this unit.